All right, lesson 8, free fall. So free fall is when you have a falling object and that object is only being affected by the force of gravity. So that means as the object falls, there's no other forces. Like for example, there's no friction from the air, which we call air resistance. So here's some examples of free fall. So let's say you're juggling and you throw the ball up in the air while the ball is moving through the air. So here, here, and here, and here, where I'm putting check marks, all of those are considered free fall. So I know that in your everyday life, when you think of something falling, you only think of the downward part of the motion, but actually in physics, free fall includes when the object is going up and again when it's coming back down. Now, at this moment here where I'm circling, when the juggling ball is touching your hand, that would not be considered free fall, because at that moment there's two different forces acting on the ball. There's the force of gravity pulling it down, but there's also a force from your hand pushing it up. And so gravity is the only thing that's allowed to be there. So at that moment, it wouldn't be free fall. But when the ball is moving through the air, as long as you're not touching it, that would be free fall. Another example of free fall would be if you go skydiving. As long as your parachute is not open, then the only thing really affecting your motion is the force of gravity pulling you down, and so that would be free fall as well. Some things that are not free fall would be, so if you go parachute jumping and the parachute is open, that's not free fall, because what happens is there's air resistance or friction from the air pushing you up at the same time as gravity is pulling you down. And so since it's not just gravity, that's not free fall. The other thing would be if you have an object that's rolling down a ramp, that's not free fall either, because although gravity does pull the object down the ramp surface is actually pushing up on the object, and so that makes it not free fall. So here on Earth, the acceleration due to gravity is 9.81 meters per second squared. And what this means is that when you drop any object, as long as that object is in free fall, it will accelerate down at 9.81 meters per second squared. So to give you an example, let's say you drop a hammer and a feather. Now let's say you go and you do this in a giant vacuum chamber. So a vacuum chamber is like a room where there's no air. Okay, so when you drop the objects, there's not going to be any air resistance. What will actually happen is that the hammer and the feather will both fall at the same rate. So if you drop them from the same height, they'll hit the ground at the same time. And as they fall, their acceleration is both 9.81. Okay, so it doesn't matter what the object in the question is. If you're doing a question involving a falling object in Physics 20, you know that the acceleration is going to be 9.81 meters per second squared down, which we're going to write as negative 9.81 meters per second squared, because down is one of our negative directions. So just some hints when you're doing the free fall problems. Some of the problems will mention that an object is dropped. Now, when you drop an object, the moment it leaves your hand, the initial velocity is 0. So VI is 0. As I was just saying, the acceleration is going to be 9.81 meters per second squared down, or negative 9.81. And VF, which is the final velocity, just so you know, it refers to the object's speed just before it hits the ground. So VF is not 0, because we know that when the object hits the ground is going to stop the object, right? So it's tempting to say that VF is 0, but that's not what we mean. VF is just before the object is stopped by the ground. How fast was it going? And then we have thrown objects. So if you have an object that's thrown, okay, whether it's thrown up in the air or thrown down towards the ground, in both of those cases, VI is never 0. Okay, when you throw the object, you're giving it some initial speed with your hand. If you throw an object up in the air, the speed will be 0 when the object reaches its maximum height. So if I throw something up in the air, okay, it's going to go up, it's going to reach some maximum height, which means it's the highest it can go, and then it's going to come back down. At the point where it's the highest it can go, the speed is 0 for just a split second there. And if you throw an object down towards the ground, then VF refers to the object's speed, again, just before it hits the ground. And just like before, the acceleration is still negative 9.81. So in all the questions we do, the acceleration is going to be negative 9.81. Okay, so let's do this example here. So Sally drops a penny from a height of 10 meters above the ground. How long will it take the penny to hit the ground? So first thing we're going to notice here is it says Sally drops a penny. So from the slides we just looked at, we know that the initial speed of this penny is going to be 0. Now she's dropping the penny from 10 meters above the ground. So the displacement that the penny is going to go through is going to be 10 meters down. Okay, so we're going to write -10, right? Because the penny is falling down 10 meters towards the ground. We want to know the amount of time, so t is our question mark. And then because this involves a falling object, we also know the acceleration. So the acceleration is going to be -9.81. Now, these questions are actually just like the ones you were doing in lesson 6. So it's still just an acceleration problem. So we're going to pick out one of our accelerated motion formulas. And remember, you're going to look for a formula that has these 4 variables in it. We don't know what VF is, right? The question doesn't ask us for VF. It doesn't tell us what VF is. We really don't care about VF at all. So when you're choosing a formula, don't choose one that has VF in it. Pick a different one. And when I look on the formula sheet, I see this one here. So D is equal to VIT plus 1/2 AT squared. That has everything in my variables list in it, and it does not contain VF, so that's looking good. Now, there's a trick you can do here which is going to make this easier. So because VI is 0, that means this entire VIT term is also going to be 0. So the formula really just becomes, if I rewrite it here, D is equal to 1/2 AT squared. Okay, so we're looking for T. So let's rearrange that formula. So let's multiply both sides by 2, so that gives us 2D. Let's divide by A, and let's square root. Okay, and then now we're good to plug in our numbers. So we're going to have 2 times -10 divided by -9.81 meters per second squared, all under square root. Now you should try putting this in your calculator just to make sure that you're getting the same answer as me. But when I do this, after rounding to 2 significant digits, I get 1.4 seconds. Okay, example 2. A student throws a tennis ball upwards with a speed of 2 meters per second. How far upwards will the tennis ball move? Okay, so this time the object is being thrown. So remember, VI is not 0. In fact, here, VI is going to be 2 meters per second up. So because it's up, we'll make it +2. So anything that's going up is positive, anything that's going down is negative. And we want to know how far, so we're really looking for D. Now, it might seem that that's all of the information that the question gives. But remember, since this is a free fall question, it involves an object moving through the air, we actually know the acceleration. So we can write down the acceleration is -9.81. Now notice here, the tennis ball is moving up, but the acceleration is still negative, right? That's because gravity is what's causing this acceleration, and gravity pulls all objects down, right? Whether those objects are moving up towards the sky or down towards the ground, gravity always pulls them down, so this acceleration is always negative. Now, there's one other thing we know here. It doesn't tell us in the question, we just have to know this. We have to know that when this tennis ball gets to its highest height, the speed is going to be 0, right? So if I draw a little picture, here's the tennis ball. When it leaves my hand, it's moving up. It goes up, and as it moves up, it's slowing down. Eventually, it gets to some highest point up here, and at this highest point, the speed is 0, and we're basically asking for this distance or displacement. All right, so this time, if I look at my variables list, this time I don't know T. T is not given, T is not asked for. So when I find a formula, I'm gonna look for one that doesn't have T in it. So take a sec to think about what formula that might be. Pause the video if you need to. And the formula that does not have T is this one here. VF squared equals VI squared plus 2AD. And we're gonna rearrange that for D. So first let's subtract on both sides by VI squared, and then let's divide by 2A. Okay, so we have VF squared minus VI squared over 2A equals D. And let's put our numbers in. So VF squared is 0 squared. Now this time I'm not gonna cross the 0 out like I did in example 1. I'm just gonna plug it in. So I'm gonna have 0 squared minus 2 meters per second squared all over 2 times negative 9.81 meters per second squared. Okay, now before we put this in our calculator, I want to point out just a couple things. When you have more than one thing in the denominator or on the bottom of the fraction, so see how here I have this 2 and I also have the 9.81. When you put that in your calculator, you need an extra set of brackets, okay? Because otherwise the calculator doesn't know that both things are on the bottom of the fraction. So we need to put another bracket in front of the 2 and another bracket after the 9.81. Okay, so brackets around the entire bottom of the fraction, otherwise it's not going to work. The other thing I just want to point out is the difference in the squares here. So notice this square that I'm putting a purple box around is outside the brackets. Okay, what that means is that that square applies to everything inside the brackets. So it means this square applies to the seconds, it applies to the meters, and it also applies to the 2. So when we do the top of that fraction there, it's going to become this. So 0 squared is just 0, minus 2 squared is 4, and then we end up with meters squared over seconds squared. Okay, and then on the bottom, if we have a look, well, I'll use a different color, I'll use green. This square that I'm putting a box around is inside the bracket, which what that means is that that square only applies to the seconds. It doesn't apply to the meters, and it also doesn't apply to the 9.81. So when I'm putting the bottom part of the fraction in my calculator, I'm not doing 9.81 squared, right? The square is just on the unit. I'm just typing in 2 times 9.81, and that gives me 19.62. So the units, or the number, I should say, on the bottom here is 19.62 meters per second squared. Okay, so now if we put that in the calculator, we are going to get, or actually it was negative 19.62, sorry, because it was 2 times negative 9.81. So now if I put that in the calculator, after rounding to 2 significant digits, I get 0.20 meters. And for the units, I'll just show you quick. So up top we have meters squared per second squared. That's being divided by meters per second squared. Remember, we don't cancel units when we have a division sign, so we turn it to a multiply sign and flip the second fraction. And then now we can see that one of the meters up top cancels the meters on the bottom, second squared cancels second squared, and so that's where meters in the answer comes from. Okay, so for example 3, it says if Michael Jordan can leap 1.29 meters in the air, then what is his hang time, which is his total time spent in the air? So for this one, what we're going to do is we're going to split the question into 2 parts. So if we have Michael Jordan here, okay, he's going to jump up in the air, he's going to reach some highest point, and then he's going to come back down to the ground. We're going to consider the part where he's moving up in the air separate from the part where he's moving down towards the ground. So basically we're splitting this in 2. So we're calling this part where he's moving up part 1, and then the part where he's coming back down to land part 2. Okay, so let's look at part 1 where he's moving up first. Now when you jump in the air, what you're really doing is you're sort of throwing yourself in the air, you're launching yourself. So VI is not 0. But something is 0 in part 1. Think about what it is. And if you said that it was VF, that's perfect, because when you reach your maximum height at the end of part 1, that's where you're not moving for a split second. Now on the way up, Michael Jordan moves 1.29 meters up in the air. So we'll call it positive 1.29. And we're looking for the time, so we'll make T our question mark. And then think about what the other variable I can use is. I don't know VI because I don't know how fast Michael was going when he left the ground. But we do know that because Michael Jordan is going to be moving through the air, that this is a free fall question, so the acceleration is negative 9.81. Okay, since we don't know VI, don't pick a formula with VI in it. So instead, we're going to use this one here. So we have D equals VFT minus 1/2 AT squared. And like I did in example 1, since VF is 0, I'm going to recognize that that makes this entire first term 0. I'm going to cross out VFT. Now, the formula becomes this. D equals negative 1/2 AT squared. So the negative in front of the 1/2 AT squared, that doesn't go away just because you cross out VFT, okay? It still has to be there. Okay, so let's solve for time. So again, we're going to multiply both sides by actually -2 this time because I want to get rid of the negative 1/2. So negative 2D. I'm going to divide by A now and square root, and now that's going to be equal to T. And so I'm going to put my numbers in down here just because I'm running out of room. So T is -2 times 1.29 meters over -9.81 meters per second squared. And when we put that in our calculator, we're going to get 0.5128. And then I'm just going to write ... because the number actually keeps going after that. And just want to remind myself that I haven't written down the whole number. Now, that's not my final answer to the question, okay? So I'm not rounding that number yet. We don't round until we get to our actual final answer. What we have to recognize here is that the amount of time that it takes for something to go up in the air is equal to the amount of time that it takes to come back down. So if Michael Jordan takes about 0.5 seconds to go up, he's also going to take 0.51 seconds to come back down. So the total time is just going to be double the time that we just calculated. So it's going to be 2 times 0.5128 ... Now, when you reuse 0.5128, make sure you type in all the decimals that come after the 8. Don't round anything too early or you're going to get a rounding mistake on your final answer. And so after doing this, I get 1.03. That is already rounded to 3 significant digits. So there we go. Now, by the way, you can only do this thing where you multiply by 2. So right here where I'm circling in red, you can only do that if it's a symmetrical situation. So by symmetrical, I mean in this question, Michael Jordan goes up 1.29 meters, and then he also comes down 1.29 meters. But what if you had a situation like this? Okay, so let's say I had a cliff with some water down below, and let's say I'm standing on the edge of this cliff, and I have some kind of object in my hand. I throw the object up in the air. The object goes up, and then when it comes back down, it falls into the water below. Notice now the distance that the object moves up is different than the distance that it moves down, right? It falls down a lot farther than it went up. And so this is not symmetrical, so you wouldn't be able to just take the time for the first part and multiply by 2. Instead, what you would do is you'd set up one equation for this part, we'll call that part 1, and that would look like what we were just doing in example 3. And then you would set up a different equation for this part, we'll call that part 2. You calculate the time for part 1 and also the time for part 2, and then add them together. And that's the end of lesson 8.